Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we explore section 8.5 in the Big Ideas Math Integrated Math 2 textbook, proving triangle similarity by side, 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 and side, angle, side. Now those are ones that you've heard for triangle congruence as well, but these are slightly different because sides are no longer congruent in these cases, they are proportional. So those proofs can be a little different, and I don't know if we do proofs, this like two-column proofs, this kind of thing. These are the ones that can be a little iffy for me because it's how the book teaches it, and it's not just like reflexive property, shared side, or something like that, or given, and things like that. So we'll see what they do with it, but you did see angle, angle already before, and I do believe this one lends itself pretty closely to the angle, angle thing, because these are the two other ways that you prove triangles are similar to each other. That's why I thought 8.4 should probably have blended with these ones a little more, and it shouldn't have been with that quiz on 8.1 to 8.3, but you know what, it's neither here nor there. We are here now. Let's go ahead and take a look at the lecture portion before we then dive into the problem set, which I believe is short. I think it only goes to 24 problems. They may be long, but your problem set may be shorter, and the drill and kill hopefully is pretty good when it comes to setting up proportions for problems, which I believe it is that you're going to do. Check out the description section down below if you want to find the PDF of section 8.5 down there, as well as the timestamps to every part as we begin with the lecture and then do the problem set thereafter. Let's go ahead and take a look at what that lecture looks like to begin with. We're going to be using side, side, side similarity theorem and side, angle, side similarity theorem, with previous terms being about similar figures, corresponding parts, and parallel lines. So we'll see what they say about that. For 24 problems, I doubt there are too many proofs, or I doubt there are too many graphs, or whatever, too many constructions. I think it'll mostly be drill and kill, but they do what they do, and we'll let them do it. Using the side, side, side similarity theorem. In addition to using congruent corresponding angles to show two triangles are similar, angle, angle, you can use proportional corresponding side lengths. Now, side, side, side means if the corresponding side lengths of two triangles are proportional, then the triangles are similar. You need all three sets of sides to be in proportion with each other. They need to share the same scale factor, blah, blah, blah. And you have to have parts that correspond. So AB divided by RS, let's say that that's 2. My famous example is the same as BC over ST and the same as CA over TR. If that's true and they have that similarity ratio in correspondence, then triangle ABC would be similar to triangle RST. There's a proof on page 495. That might be this page. I have no idea. Again, it's not triangle congruence, number one. And number two, this is unique to triangles, not to like quadrilaterals and other things. So this is very specific to those ones, and we can use it. We can use it. Okay, so let's use this as an example. Are these triangles, is either triangle DEF or GHG similar to triangle ABC? So what their test is going to be, and it's a pretty unique kind of test as far as how you need to do it, because we don't have any congruent corresponding angles to figure out which things line up with each other. We have to figure out which sides line up with each other. Maybe the drawing is helpful for you and maybe it's not. So it looks to me like, based on the appearance of the drawing, that this looks like a rotation, like DE should go with AB and DF should be down here and stuff. It may be, but what you really want to go by, and they actually color coded these, maybe they'll do that in the long run, so this would be extremely helpful. But what you're really showing here is testing sides based on their lengths. 6 is the shortest side in this triangle, and 8 is the shortest side in this triangle. If there's anything to show in proportion, 6 would be with 8. 6 would correspond with 8, DE with AB. 12 is the longest side, 16 is the longest side here, so you would correspond DF with AC and do that proportionality test, and then this green 12 with the green 9. And look, this has a 12 and this has a 12. Just because they're congruent doesn't mean anything to us. It actually, you probably want to stay away from that. These triangles are different sizes, so who cares if those are congruent? They are not likely corresponding when it comes to a proportionality test. So they do test to see from big to small what 8 over 6 is, 4/3, what 16 over 12 is, and what 12/9 are, and they're all 4/3. They all are in proportion with one another. They all share the same similarity ratio, or they share a similarity ratio. Therefore, these two triangles, yes, are similar, ABC and DEF. Now, this wouldn't be a good example unless the next one doesn't work, so let's see how the next one goes. Let's check and see how GHG does with it. We'll test 8 to 8, which is kind of a big red flag to us. It's the shortest sides in both of them, but you can see already 10 would go to 12 and 16 with 16. So 8 with 8, 16 with 16, great, but 10 and 12 are not the same. So you can tell here as they do this test that 2 will be in proportion 1 to 1, meaning the triangles would be congruent if these sides were congruent, which they're not. You get a similarity ratio of 6/5. Ratios are not all equal, so they're not all in proportion, even if 2 of the 3 are. So triangle ABC and triangle GHJ are not similar. And again, you know which ones you're testing. I'm just going to say not similar overall. So, because they're not corresponding with each other truly if they're not in proportion either. So there's that. All right, so that's the kind of test that you can look at there. Here's another set of side stuff. This is the proof. This is the proof of the side similarity theorem. Let's see what they say. We're going to prove that triangle JKL is similar to triangle RST using side. In order for them to do this, it looks like they're going to prove two triangles are congruent first, and like by redrawing a new triangle here. They are, excuse me, they're locating point P, on segment RS so that this is the same length as this. And then they're drawing a parallel line PQ right here so they can then triangle RST is similar to triangle PSQ by angle. So you can use angle because of what you've kind of seen before. Corresponding angles congruent here, reflexive property here. I mean, different kinds of things. But once you've drawn them parallel, you've made them similar. Maybe they'll go the other way with this. But then you have a similarity ratio PS to RS, PQ to RT, and QS to TS, things like that. You can use the given proportion and the fact that PS is equal to JK. So those are equal. To deduce that SQ is equal to KL and QP is equal to JL. Sorry about all the stuff I'm doing there. By the side congruence theorem, it follows that those two triangles are congruent. Finally, we use the definition of congruent triangles in the angle similarity theorem to conclude that those are similar. Kind of a wonky proof. I'm not saying it's a bad proof. It's hard to follow as far as what they're actually saying. They're basically saying make one the same, map this onto this, but give it a different name, and then because this one's similar, then that one's similar. But it's kind of difficult to follow, and I'm sure they're going to make us prove one of the other ones at some point, so I'm going to do my best with it. These ones are not quite as straightforward as triangle congruence. I'm going to say that. They say the parallel postulate, here we go. The parallel postulate allows you to draw an auxiliary line PQ in triangle RST. There's only one line through point P parallel to RT, so you're able to draw it. So whenever you draw this, that's known as, not by construction, but the parallel postulate. Okay, using the side similarity theorem, they say find the value of x that makes triangle ABC similar to triangle DEF. So this is one of those things that kind of, you're doing the same math, even though they're asking a different question. They're saying what would make these similar is all these sides would have to be in proportion with each other. So you still build out a proportion however you best can to make this so. They are going off of, what's their first one? Finding BC. So they're finding BC using this x minus 1 here. And they're comparing x minus 1 to 18, two parts that correspond. Note that even though they're drawn the same way, apparently, they also give you letter order. So you know that BC, 2, 3 letters should correspond with EF, letters 2, 3. X minus 1 over 18 equals, and they went for 4 to 12. I would have loved to go with these two, but it probably would have led to a quadratic. So they're going straight for this one first. Oh, they just say solve for x. They don't need to say find, well, they say solve for x. So yeah, I actually like this one. So 4 to 12. So they're going boom is to boom, like that. And then they cross multiply and solve, they get x equals 7. Now, they're also, after that, showing that x equals 7 works with this by substituting 7, not only here to get 6, 6 to 18 is 1 to 3, but also right here, 7 plus 1 is 8, times 3 is 24, and 8 to 24 is also the same. So they all check out, they all get a 1 to 3 similarity ratio, and it all works. So basically just using that, just setting up proportions and making it work. That's no different from what we would do generally. Okay, and then the side angle side similarity theorem. It's like side angle side triangle congruence, where in the triangle congruence one, two sets of sides are congruent and the included angle, the one in between them, is congruent. Now in this one, two sets of sides are proportional with the included angle congruent, but you do need proportionality of the other two. So here's an example of them. If angle X and M are congruent, and then these two share proportionality, ZX, I'm going to kind of do this thing, ZX with MP, or PM, and then XY with MN, not congruent, but share proportionality, then they are similar triangles. And those are the different three that we have. We have angle, angle, side, 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 and side, angle, side. There is no angle, side, angle. There is no HL version. I'm sure there's something you can do among them to make it so, especially with HL, but it would still be a proportionality thing if you did. And the reason there's no angle, angle, side is because angle, angle is already enough. You don't need a set of sides proportional with that. There's a proof on another page. I don't know if it's part of our notes or something we'll have to do. So let's use this theorem, look at this probably last example, and then we'll move forward. You're building a lean-to, I thought this was like a bike ramp. You're building a lean-to shelter, starting from a tree branch, as shown. Can you construct the right end so it is similar to the left end using the angle measure and lengths shown? So what they show you here is two sets of sides and the angle in between, two sets of sides and the angle in between. It looks like they're going to kind of show that these two, wait, can you construct the right end so it is similar? Oh, maybe something's broken proportionally. I don't know what they're actually saying with this. Can you construct the right end so it is similar? Okay, let's see what they say. Both measures of angles A and F are equal, so A is congruent to F angle-wise, and then we compare these proportionality. We go 9 to 6 for these two parts that correspond. That's 3 to 2. 15 to 10 is 3 to 2. Oh, they're saying, is it possible to do so? I thought they were saying, can we come up with numbers? Got it. So is it possible to make this similar here? Yes, by proportionality and congruent angles, you have side angle, side similarity. So these two triangles are similar. So yes, you can make the right end similar to the left end of the shelter. It's possible. Kind of a weird question. I thought they meant, can you generate numbers with this thing? Okay. And then there are just some other ones to do stuff with. And I'm not going to as I move forward to the problem set. So 12 minutes through, let's go ahead and look at the vocabulary and core concept. Check. Number 1, complete the sentence. You plan to show that triangle QRS is similar to triangle XYZ by the side-side-side similarity theorem. Copy and complete the proportion you will use. Now I don't have to copy it. QR are letters, let's just write 1, 2, 3 and 1, 2, 3. QR are letters 1 and 2. XY are letters 1 and 2. They need to have a similarity ratio that is equal to, now we got to go to triangle QRS. YZ was 2, 3. RS is 2, 3. And then QS is 1, 3 and XZ is 1, 3. Now you might ask, can I write SR? Can I write YX? Can I write ZX? Yes, you want to tend to put parts that correspond so that you follow that letter order. But yes, you can. It's still that length. Length of XY and length of YX, same thing. Number 2, which one doesn't belong? Which triangle does not belong with the other 3? Explain your reasoning. Looks like it's going to be a proportionality test, so it may take a little moment to figure this out. Let's say that this one's triangle A. Let's test the other ones against triangle A, see if we have any similarity there. If we find one that's different, we'll call it B. So we got to go by and notice that they don't change the different colors of these, so we got to find kind of shortest side with shortest side, things like that. So among these ones, 3 is the shortest side, as is 6. We'll see if 3 over 6 is the same as 4 over 8. Yes, those are both 1/2. And 6 over 12. Yes, that's also 1/2. So that all checks out. Those are the same. So this is another A, if you will. These triangles are similar using side, side, side. They didn't do any side angle side on these sets. 9 is the shortest side here. Test that against 8. Interesting test. 9 is to 8 as 12 is... Oh, I'm sorry, 9 and 6. 8 is not the shortest side. That makes more sense. 12 over 8. By the way, these are both 3 over 2, 3 over 2, 1.5. And 18 over 12, that's also 3 over 2. That one also checks out. So this is another A. Unless I'm seeing something incorrectly, it looks like this one will be different. So 4 goes to 8. Well, check this out. 4 is the shortest side like this one was, but then 8 and 6 are different. Oh, I'm sorry. No, it's not. This was the shortest side. Let's move forward. 4 goes to 8. That's 1/2. Oh, to 6. 6. Darn. 4 goes to 6. That's 2/3. I'm no good at comparing side lengths. 6 to 8 is 3/4. That doesn't work, and there's no need for me to test. I will, but there's no need for me to test it. Well, actually, Let me just say it out loud. 8 to 12 is 2/3 as well, which would match the 4/6. But this one breaks it. This one breaks it, and it doesn't show proportionality in that sort of way. So this one's B. My reasoning is in my proportionality. It is not similar using side, side, side. Not similar by side, side, side. It's not that there's not enough information. It's that they're actually not similar. Okay, so those are the first two problems. That is the beginning of this, and we have problems 3 through 24 to do here. So I'm going to go ahead and get us started. Again, you can print these things out or access these for yourself. Grab a piece of binder paper. I don't know if we'll need graph paper for this stuff, but away we go. In exercises 3 and 4, determine whether, now we kind of just did this in the first set, but determine whether triangle JKL or triangle RST is similar to triangle ABC. So on number 3, again, we're comparing side length. Well, you see things that are proportional. You see things that should correspond if proportional. You also see the letter order, JKL and RST. So side lengths need no comparison as like shortest side, shortest side. Let's just look at the ones on the left side and things like that. The way that they drew them is the way that they line up. So we're going to check and see if 6/7, this is triangle, hold on, I'm going to write is triangle JKL similar to triangle ABC. So we're going to test JK to AB, that is 6/7. Let's see if, and that's 6/7 literally. And then we get 7/8 for this next set there. Those are not the same. I don't know if you're aware of that, but those are not the same. So no for those two. Now is triangle RST similar to triangle ABC? So let's try 3.5 to 7. Now 3.5/7 is 1/2. Now let's try 4/8, which is also 1/2, and 6/12, which is also 1/2. Yes, that one does work. Let me go to bang, bang, and bing, bing. Yes, those are. I don't need to test if RST is similar to triangle JKL. They won't be, because JKL was not similar. It's like if one is similar, it's like a transitive property thing. If ABC is similar to one and it was similar to the other, then those other two would be similar to each other. Not the case and not the test requested. Number 4. And by the way, if JKL was similar to RST, that's no guarantee that those are both similar to ABC. So that's why we test those in that way. All right, number 4. Is triangle, now these ones are not drawn the same way. So this one requires that you do a little bit more with respect to looking at the side lengths or literally. And here's the thing. They are actually asking triangle JKL to RST. So as much as I want to compare side lengths, they better line those things up the same way. As in, if JK is the shortest side, AB better be the shortest side. Otherwise, there's no reason to do a test. You don't just do shortest side to shortest side if they're giving you the similarity statement. So JK itself is 20. And AB itself is 16. Those are both the middle side lengths, if you will. They are the ones that are not the shortest or the longest. So it's good that they're doing the test that way. And I think they're going to keep it like that. So let's do 20/16, which is 5/4 as a reduction. Divide those by 5. 5/4. Let's try JKL. KL is 17.5. And BC is 14. Those are the shortest sides. I don't know if that's true or not yet. I'm going to set this up first. And then JL is 25 and AC is 20. I know these are both 5/4. Those are both good. The question is 17.5/14. I believe that's correct because I can divide these by 2.5. Divide this by 2.5 and you get, no, 3.5, excuse me. Divide this by 3.5 and you get 4. Divide this by 3.5 and you get 5. So they're all 5/4. Let me just say yes. And I probably should have done this before. Ratio is 5/4. Let me write that on this one right here. Ratio was 1 to 2 on that guy. So cool. Now that's kind of part A. We still need to figure out triangle RST. It's likely to be a no, but you never know. Is triangle RST similar to triangle ABC? Let's try RS with AB. RS is the middle one, as it should be. So 12 over 16. That's 3/4. Let's try ST, 10.5, with BC, 14. I don't know yet. 3/4, I think so. I think so. And let's try RT, 16, with AC, 20. I think it's 4/5. So no for that one. Different ratios, right? These are both 3/4. If you divide this by 3.5, you get 3/4. Divide this by 4, you get 4/5. So not similar. Now that was a side test. In exercises 5 and 6, find the value of x that makes these two triangles similar. So now we know that they're going to be similar in these sets of problems, and it's just the test to make it so. And we can choose our things to solve for x however we like. To humor you, I might do both of them for this specific problem. In the next one, I likely won't. But here you see DEF, and XYZ. Looks like they are oriented the same way. So we know which parts correspond, the left side, the right side, and the bottom side, and things like that. So it looks like we have a good old 10 over 5. Well, actually, let's write this first. Let's write 2x minus 1 over 14. I'm making my choice in the right side, to the right side, something with x in it. And let's do the left side, 5 over 10. Something popped up on my screen. Hold on. 2x minus 1 over 14 equals 5 over 10 is a thing that we can use. We can reduce 5 over 10 to 1/2, and I'm going to do exactly that. 2x minus 1 over 14 equals 1/2. And then I'm not even going to cross multiply. I want to just multiply by 14. 2x minus 1 is 14 over 2 times 14 times 14, and that's 7. Then I get to add 1 and divide by 2, and you get x equals 4. Now from here would be enough to be able to double check everything and see that it works. To show you another proportionality, as you say, what about 5x plus 2? Why didn't you do that? Well, we could. Let's do 5x plus 2 over 11. Notice this is the bottom on the big divided by the bottom on the small. And let's do the left on the big, 10 over 5, over the left on the small. 10 over 5. And 10 over 5, as you know, is 2. So let's do the same thing as we were doing before. Whoops, over 11 is 2. Multiply both sides by 11. And here we get 5x plus 2 equals 22. 5x equals 20. Divide, and you get x equals 4. That seems to pan out alone. It's probably not worth doing that next part. To show proportionality, I can confirm that my answer is what it is from that. Remember, you really only need to do one or the other, but this seems to work out. And to just double check, the length of EF. EF is 2 times 4 minus 1. 8 minus 1 is 7. And XZ, the length of XZ, is 5 times 4 plus 2. 20 plus 2 is 22. So let's see if all that pans out. And then after that, I probably will do a little less testing. Let's see that 5 over 10 equals, I got to do EF, 7 over 14. Those are both 1/2. And 11 over 22, also 1/2. That does check out. The ratio is 1 to 2 for all those, yes. So on the next problem, number 6, I'll do the same thing. However, I'm only going to do one test to solve for x, and then I will plug them in and see if they work. Assuming that they are, they're two different things that have x's in them. I'm going to be wisest. So, by the way, DEF and XYZ looks like a rotation, if you will. So the x minus 1 corresponds with the 10, whereas the 3 times x minus 1 corresponds with the 7.5. That's by the letter order and by the appearance. I'm going to not do the 7.5 if I don't have to. The bottom has the 4 here, and the top has 8 here, and I kind of want to use those two as well. So let's do x minus 1 over 10 equals 4 over 8. That will be my test here. For the sake of just diversity, I'm not going to reduce this to 1/2 this time. Let's actually even cross multiply and say, because maybe you're familiar with that. If I do 8 times x minus 1, I get here 10 times 4. There's my cross multiplication. 8x minus 8 equals 40. Add 8 and divide by 6. Divide by 8, you get 6. You'll get the same answer no matter which way you go about it. Cross multiplication or not, reducing fraction or not, dividing by 8 here or not. I do get x equals 6, and let's go ahead and find out those lengths and see if it all worked out the way we wanted it to, especially with the df. But let's start with xy. The length of xy is 6 minus 1. 6 minus 1, which is 5. And the length of df is 3 times that 6 minus 1. 3 times 5 is 15. So let's see if 4 over 8, 1/2, equals x minus 1 is 5 over 10. That's 1/2. And 15, 7.5 over 15. I ignored the 7.5 before, but now we see that it seems to work out. That's also 1/2. So yes, x equals 6 is the one that makes them similar by side, by the way. I've only done 4 problems so far. All right, in exercises 7 and 8, we want to verify that these two triangles are similar and find the scale factor of ABC to DEF. So we need to be specific about enlargement versus reduction based on what sizes are what. Now, here I'm going to copy and paste this if you don't mind. So here they have, well, actually, here's what I'm going to do. Triangle ABC, similar to triangle DEF, because there are 2 problems with it. And I'm going to rewrite things so that they go in the same order. So for triangle ABC, I'm going to start with AB. AB is 15. BC is 18. And AC is 12. What I did was letters 1, 2, then letters 2, 3, then letters 1, 3. I'm going to do the same thing here because they intentionally write things in a different order, or it looks like they do. Actually, no, they didn't. They just kind of wrote them in different spots. But in case they do mix it up, I'm going to do exactly that. DE is 10. That's 1, 2. And then 2, 3 is EF is 12. So it looks like they did put things that correspond with each other, just in a different order. And DF equals 8. First things first, from ABC to DEF, it is a reduction. They do want the scale factor. They said verify these are similar, so they will be similar. But they want the scale factor from one to the other. That means we have to do this divided by that. We want to see that 10 over 15 is the same as, well, here, let me just write this. This is 2/3. 12 over 18 is 2/3. And 8 over 12 is 2/3. So that is the verification, and the scale factor K is 2/3. So they're all in proportionality with that. There's number 7. Let's do number 8. You know, they lined these ones up. They put CA and FD as the last set, but that's the same thing as AC and DF. So AB is 10, BC is 16, and CA, or I'll put AC, is 20 because it does mean the same. Now DE is 25. Looks like an enlargement this time as we do the division. EF is 40. And FD. And by the way, these are similar. Whoops, DF. These are similar by side again. Everything we've done so far is side. If you missed the title of this or you missed the lecture portion, there's also side angle side tests as well. These are all side. So we're trying to see if 25 over 10 is the same as the others. 25 over 10 is 5/2. 40 over 16, divide those by 8, you also get 5/2. And 50 over 20, divide those by 10, you get 5/2. So that all checks out. They are similar, and your scale factor is 5:2 as it is an enlargement. Okay. In exercises 9 and 10, determine whether the two triangles are similar. If they are similar, write a similarity statement and find the scale factor of triangle B to triangle A. Oh, they're marked right there. So B to A. This one looks now like the side angle side similarity tests where the included angle the one in between the two sets of sides that you test for proportionality must be congruent to each other, like the angle D and W. They say determine whether they're similar. What I'm really trying to see, and listen, I'm going to begin with what similarity statement I'm trying to do. So I want to ask myself, is triangle, now I'm going to put the middle letter D and W. I'm not saying is this triangle similar to this triangle, they're called A and B, but W is the middle letter here. Let's do F to D as the longer known side, and therefore I'll do Y to W as the longer known side on triangle B, and then D to E here, which means this is W to X right there. Here's the question. Are those two similar in that way? And and as we're doing that test, we have to test things that, let me just leave it as it was. As we're doing that test, those are the sides we have to test that are proportional. As we know that angle D is congruent to angle W. That's a check for angle. And now we need to see if FD 12, triangle B to triangle A. Okay, so if 12 over 9 is the same thing as 12 over 9, 8 over 6. 8 over 6. 12 ninths is 4 thirds. 8 6 is 4 thirds. Divide these by 3, divide these by 2. So K is 4 thirds. So yes, that one checks out as well. So yes. Yes. And they said write a similarity statement. I already did before. Triangle FDE is similar to triangle YWX. I guess I'll save that for next time. So are they similar? Here's your scale factor from triangle B to triangle A. B to A was an enlargement. Number 10. Okay, in number 10, you again have a set of congruent angles. I'll go straight into it. Measure of angle T is the same as the measure of angle L. So angle T is congruent to angle L. They both are 112 degrees. And there is a set of congruent angles. It is the included angle of the set of marked sides. You are going to compare side lengths based on which ones are comparatively longer and comparatively shorter. Now, our scale factor test is going to be from triangle B to A. So this looks like a reduction, if it's indeed true. We're going to test and see if 8 over 10 equals 18 over 24. Well, 8 over 10 is 4/5. 18 over 24 is 3/4. They are not the same. These triangles are not similar. I know they probably want us to make a similarity statement, if you will. You can't make one if they're not similar, but which triangles were we testing for? Obviously B to A, but is triangle JLK similar to triangle RTS? No, they're not. That was the test we went for. It didn't work. Oh, I didn't mark number 10. I apologize. That was number 10. Okay, let's go to exercises 11 and 12. In exercises 11 and 12, sketch the triangle. Oh, did I? Okay, I didn't have to sketch these ones. This looks the same as the last one, but sketch the triangles using the given description, then determine whether the two triangles can be similar. So let's do a sketch in triangle RST, and I'm not drawing this to scale. And I think that's more helpful that we just write things as they are. Triangle RST, the length of RS is 20, the length of ST is 32, and the measure of angle S is 16 degrees. Clearly not drawn to scale. In triangle FGH, I'll at least draw this one bigger because they look to have, In triangle FGH, GH is 30. I'm going to change the letters. I thought they were going to say RST is similar to FGH. So look at this. Our known side, and H is 24 degrees. You know what? Okay, let's keep it. FGH. I don't yet know what they're going to say about it. GH is 30. HF is 48. And measure of angle H is 24 degrees. Now they're asking if the triangles can be similar. I I mean, it could be possible. We don't have enough information. I'm going to say that with certainty. Here's the concept, and I'm going to kind of exercise this triangle within. If the triangles are similar, then that means that this length needs to be longer, than the other two here, because this was longer than those and all that. And then this would have to be 16 degrees here as well. 24 plus 16 is 40, minus 180 is 140. This would have to be 140 degrees, if so, which means so would this. Now I'm just exercising everything throughout in 24 degrees. And if they share a similarity ratio, 32 over 30, 32 over 30 is 16 over 15. 16 fifteenths of 20. 16 fifteenths of 20 is, I don't know, some weird number. 4 thirds times 16 is 64 thirds. This would have to be 64 thirds. And 15 sixteenths of 48, that's a cleaner number. That's 45. So that would have to be 45. If the triangles were similar, this would be the setup. 20 plus 32 is more than 45. That pans out all right. And these would be the angles. It's possible that they can be similar. There's nothing that interferes with it. Yes, it's possible. And it would be in this specific way, I suppose. I can't think if there is another way that it can work, but triangle RST is similar to triangle FGH. Again, there's nothing that says it's not possible. Is it a guarantee? No, there's just not enough information here. We don't have a side angle side thing. What you're not doing is I was going to align this angle with this angle, but they're not congruent, and I didn't see that they weren't talking about the same two angles. So I was going to put 30 here and 48 here. So listen, it's possible. I just don't have the information to be able to spell it out for you. So, we're just going off that. Now, ST was 32. Okay. The only other question. RST and FGH. Sketch the triangles using good description and determine whether the two triangles can be similar. So I don't see why they can't be similar given all that I have, basically. Oh, one last thing I want to check? You know what? Actually, this won't be possible. Hold on a second. Let me look at this. Sorry, I was trying to look at the things and how they align. I see RST and FGH. That's the order that they give. Here's the problem with this. I checked triangle inequality theorem. That was good. But that, I forget if it was hinge theorem or whatever it's called. Opposite the 140 is 30. And that's not the longest. This is the biggest angle. That's not the longest side. So I'm just going to wipe that out and say not possible. They don't ask me to explain why, but I'm going to explain to you why now that I just said all that. 140 is the biggest angle measure, so 32 has to be the longest side, but it's not. And 16 is the smallest angle, 45 would have to be the longest side, so it's not. Opposite largest angle isn't longest side. So forget what I said. Now that I looked at that thing. And vice versa, all those kinds of things. So, okay, that one didn't work. Interesting. I don't know how they wanted me to actually come up with it, but my test for those angles and stuff didn't really pan out the way I wanted to. All right, number 12. The side lengths of triangle ABC are 24, 8x, and 48, and the side lengths of triangle DEF are 15, 25, and 6x. Once again, I don't know which parts we're actually comparing, so I'll just draw some things and see if it works out the way that we want it to. I don't know yet, but this is going to be a side test if we do. So they don't say which ones are which. I'm just going to kind of bring some into the fold. 24, 8x, and 48. Now, at best, what I can do here, to my knowledge, DEF. That's a D. For triangle DEF, best I can do is 15. I'm going to try 15, 25, and 6x and see that that works out already the way that it is. I do want to put 15 potentially. Okay, I can't pair 15 with 48 because I know 25 is a longer side than that. I don't know if 25 should go here. I also don't know, because here's another possibility. Let me show you this one. Given that ABC is how it is, I could put possibly 15, 25, and 6x. Because here's the thing. 24 to 48 that's double the length. So 6x to 25 would have to be double the length, or 15 to 6x would have to be double the length. I don't know how this x thing works, so I don't know which one to do yet, but let's try both sets of tests and see how it goes. But 15 can't pair with 48. 25 can't pair with 24 for the same reasons. Let's try both of these. Let's start with this one in blue, if you will, because I actually don't know. I'm not sure. And this one will be a green test. Let's see how 15 to 24 works alongside 15 to 24 and 25 to 8x. Okay, let's see how that one works. 15 over 24 also reduces, dividing by 3 to 5/8. And 25 to 8x here. Let's cross multiply and solve for x. You get 40x equals, and 8 times 25 is 200. Divide by that, you get x equals 5. Now with x equals 5, let's substitute in here 6 times 5. So now these are in proportion, right? 8 times 5 is 40. So 24 to 40 and 15 to 25. Let's check out 6x. 6 times 5 is 30. Is 30 over 48 the same as 15 over 24? 30 over 48, you can divide those by 6 and you get 5/8, and that works out because that's also 5/8. That checks out. So this would work. Let's see if this other one works. Let's try the green and see if we can do the same kind of thing with the test. Let's do 25 to 48, which I do not believe can reduce. 25 over 48 equals, let's try 8x and 15 over 8x. No, we did 8x last time. Let's do 6x over 24. Now, though this one can't reduce, this one can reduce to help me some. I can divide these both by 6, and I get x over 4. So now I can multiply both sides by 4. So x is 25 times 4 over 48. This won't be a clean number. 25/12. X is 25/12 in that regard. Let's see if this actually works out, though. Let's see how 8x, 8 times, this is like the BC. BC is 8 times 25/12, which is, 8/12 is 2/3, so 50/3. So the question is if this is 50 over 3, does 15 divided by 50/3 equal the same thing as 25 over 48? I don't think so. 50/3 is close to 16. And I want to make sure I did that right. 8/12 is 2/3, 2/3, and then it's 50/3. So that's close to 16. We can also write that as 45 over 50, which is also 9/10. And that's not the same as 25 over 48. So as far as tests go, triangle ABC looks to be similar to triangle DEF. And they didn't ask which order. I just tried to work this out. Triangle DEF, if you put it in this way, and the scale factor would have to be 2/3. I probably should have known that they're going respectively with this, 15, 25, and 6x, with 24, 8x, and 48, but I wasn't certain. I don't know how they're trying to trick me with this problem. So yes, triangle ABC is similar to triangle DEF. I'm using the blue. If AB is 24, BC would be 30. I think BC was 8 times 5 is 40. BC is 48. So I might be overdoing what they wanted me to do on the problem. It wasn't very clear. And DE is 15. EF is 25. And DF is 30. So yes, those two are similar. The other test did not work. That's probably all they wanted you to do. I wasn't aware. That's okay. All right, let's keep moving to the next page. Let's go to number 13. We're about halfway through. So yeah, these problems can go as long as they have to, right? Error analysis. Describe and correct the error in writing a similarity statement. They say triangle ABC is similar to triangle PQR. A, B, C, and PQR by the side angle side similarity theorem. The problem was in their similarity statement, at least, I don't know if there's proportionality, but their similarity statement does not show corresponding parts in terms of side length proportionality. What they did was they wrote in, when they said ABC, A to B is 15, and PQR, P to Q is 24. 15 is less than 18, but 24 is more than 20. Side length compare. So I'm just going to say that. If it's true, they need to do a test with AB to RQ. They need to do 15 over 20 and see if that's 3/4, and see if that's the same as 18 over 24. That's also 3/4. So yes, that one pans out. So they are similar, and angle B is congruent to angle Q. So they need to say triangle ABC. If I say ABC, I need to say not PQR, but RQP. It is by side angle side similarity theorem. It is true. They just have PQR instead of RQP. You don't just do things alphabetically just because. You got to make sure that proper parts correspond. I think that was the quickest problem here so far. Number 14, mathematical connections. Find the value of n that makes triangle DEF similar to triangle XYZ, where this, and that. So DEF, now they give you the similarity statement, so we know which parts correspond, so I'm just going to draw them out as they are. And XYZ, I don't know if it's bigger or smaller. I'm actually not going to care. I'm just going to label. DE is 4, EF is 5, XY, which corresponds with DE, is 4 times n plus 1, YZ is 7n minus 1, and angle E is congruent to angle Y. Include a sketch. I just did. And yeah, I have no idea which ones are bigger or smaller than others because these both have n's in them. But for them to be similar, we need 4 over 4 times the quantity n plus 1 to be equal to 5 over 7n minus 1. If you'd like to ease things up, sometimes you don't know what things can cancel and not. 4 divided by 4 can be 1. So if you'd like to rewrite this, this can be 1 over n plus 1 equals 5 over 7n minus 1. Either way, cross multiplication is going to happen, right? I want to get these out of the denominators. 7 times n minus 1. Boop, boop. 7n minus 1 equals 5 times the quantity n plus 1. Let's distribute. Subtract 5n from both sides. Add 1 to both sides. Divide both sides by 2. You get n equals 3. They just said find the value of n to make this one true. This would be a side angle side test to make those in proportion, right? They would have to be equal for them to be similar. This is the value of n. And if you plug things in, 3 plus 1 is 4 times 4 is 16. So here I'd get 16. I guess that would have been bigger. And this would be 20. 7 times 3 minus 1. 16 over 4 is 4. 20 over 5 is 4. Yes, that all checks out. We're good. Okay, number 15. Making an argument. Hey, your friend's back. Because it's been like sister and cousin and things like that. Now it's back to friend. Your friend claims that triangle JKL is similar to triangle MNO by the side angle side similarity theorem. When JK, I'm going to probably draw this. Triangle JKL is similar to triangle MNO. Just make them as congruent looking as you want. Side angle side similarity theorem when JK is 18. Measure of angle K is 130 degrees. KL, why would your friend make such a random statement? KL is 16. MN is 9. Measure of angle N is 65 degrees. And NO is 8. Let's get an obvious bit, let's get one part out of the way that your friend is correct on. 18 over 9, which corresponds, is the same as 16 over 8. That is 2. However, measure of angle K, 130 degrees, does not equal 65 degrees. So here's your friend's problem. Side angle side needs the included angle to be congruent. although the side lengths are proportional, the included angles are not congruent. Now, here's the thing. I might be overstepping by stating that it may be possible that these two triangles in some form could be similar. Maybe if you do a kind of like, maybe 9's to 18, but maybe 8 needs to go over there. You know, they need to correspond differently. But the triangle statement your friend made, your friend's triangle similarity statement would not be correct. Would not be correct. That would be the exact opposite of what you'd want to say. So is your friend correct? No. Not by their similarity statement, JKL to MNO. K corresponds with N, but they're not congruent, so I don't think so. It's not going to work. All right, number 16, analyzing relationships. Certain sections of stained glass are sold in triangular beveled pieces. Which of the three beveled pieces, if any, are similar? So now we got to kind of work around some and figure out which ones are which. If you guys ever use IXL, the letters IXL, if you guys ever use IXL, there are ones I remember, I don't know if it's true for similarity, but there were triangle congruence ones where you got to find out which two of the three are congruent, and they're kind of annoying tests because you don't know which ones to go with. Here's what I'm going to look at to begin with. These are both 3's, so it's an isosceles triangle. These are both 4's, it's an isosceles triangle. These are both 3's, it's an isosceles triangle. So ones that correspond, you don't have to do all 3 sets of things. I'm just going to compare others. However, if these are both 3's and these are both 3's, and these are different values, then these ones will definitely not be similar. I'm just going to first say the purple triangle, purple is not similar to, I don't know, green, blue, teal. I'll call it teal. You guys might be seeing on a different screen. Your eyes may be different than mine. You may just say it's blue, it's blue, it's blue. I'll just call this one red. Doesn't matter. But which one would be similar to that one? I'm going to guess that it's not purple to red because 3 to 5 is not the same as 4 to 7. But is 3 to 5.25 the same as 4 to 7? That's the question. So I'll do that one first. If those other ones not similar, I'm just trying to check this one. Is 3 over 5.25, excuse me, let's do 3 over 4. Is 3 over 4 the same as 5.25 over 7? And these are all in inches, by the way. Let's make it easier for us. Instead of reducing this, let's actually cross multiply. Check this out. Let's just do 7 times 3, which is 21. And let's do 4 times 5.25. 4 times 5 is 20. 4 times 4 quarters is $1. So 20 plus 1 is 21. That one checks out. So these are in proportion. They didn't ask for the scale factor. So this must also reduce to 3/4, basically, is what I'm saying. So yeah, 21 equals 21. So the teal triangle is similar to the red triangle. And clearly the purple one will not be similar to it because it's not similar to teal. It's kind of that transitivity property thing. So these are the two that are similar, teal to red. Okay, number 17, attending to precision. Attending to precision. In the diagram, MN is to MR. Oh, okay. So interesting. As MP is to MQ, which of the statements must be true? Select all that applies. Select a reasoning. So listen, we have, I don't know if this is similar triangles, but the way that these things are drawn might throw you into a loop and to think that triangle, and I'm going to say this first, that triangle MNP is similar to triangle MQR, but that's not the case. If there's similarity, and there is similarity to be had, if there's similarity to be had, triangle MNP is similar to triangle MRQ, right? It would go that way because of this. So let's kind of redraw these. Sorry, I'm just going to redraw these completely. M on top. M, and this is going to rotate over. N, P is here. And redrawing this one, I'm not going to rotate. Well, it's going to rotate over, but it's got to reflect over. MN is to MR here. This will help us see this better. As MP is to MQ. So let's see where those angles match up because certain things aren't congruent in the way that you'd want them to be otherwise. MN has the angle 1, MNP, and then angle P is 4, and angle Q is 2, and angle R is 3. Now, M is the same in both of these. M is congruent to itself. So listen, these two triangles are similar because you have a proportionality that's true, and then M is congruent to itself. So the first thing I'm going to say, before I check anything out, I am going to say that triangle MNP would be similar to triangle MRQ by side angle side similarity. If that's true, then other corresponding angles in these similar triangles will be congruent, which means angle 1 is congruent to angle 3, and angle 4 is congruent to angle 2. Okay, let's go to the things that they're asking us which would be true. Which of the statements must be true? Select all that apply. Explain the reasoning. Angle 1 congruent to angle 2? No. You might want to say something like, oh, look, it's corresponding angles that are congruent. Well, no, we don't know these lines are parallel. You also might want to say, well, yeah, because these two triangles are similar. We also established no, because that's not the proportionality that we have. 1 congruent to 2 is no. QR parallel to NP, same thing. If we don't know 1's congruent to 2, or if 1 isn't congruent to 2, then we don't know these two lines are parallel. That's not going to work out. That's why I'm saying this drawing is misleading. What this drawing could actually look more like instead, I'm just going to kind of make something up. This drawing could look more like here's N and here's P, you know, like that, boom. And then because other parts correspond in this way with the angles that are congruent, it would be maybe more like this. So there's possibly a bend that looks like that, where R is congruent to N, you know, like that, and P is congruent to Q, kind of more obtuse, if you will. But they're not parallel in that way. So also not true. Kind of a tricky question because of the way that they drew it. Is 1 congruent to 4? I don't know. We have no reason to know that those two angles are congruent in their own triangle. M and P similar to MRQ. That's the statement I made there. So this one gives me option D. That's option D there. Reason is side angle side, and anything else that would have possibly been true would have been like not CPCTC, but corresponding parts of similar triangles. Excuse me, corresponding angles of similar triangles are congruent. Corresponding angles of similar triangles are congruent. CASTC, which I've never said out loud before. Okay, so only one of these was correct, at least known to be correct. Number 18. Are any two right triangles similar? Explain. Absolutely. Oh, are any two? No. I thought they said, is it possible for right triangles to be similar? Are like every set of right triangles similar? Not all right triangles are similar. Although they share a congruent angle pair in the right angle, the leg lengths mustn't be, is that how you spell it? Yeah, mustn't be proportional. Therefore, side angle side similarity, the side angle side similarity theorem does not always hold up. And by the way, you could figure out side by using Pythagorean theorem, but here's just an example of that. I could have 2 and 2 here, and then this doesn't have to be 4 and 4. This could be 4 and 6. I mean, whatever. They're not similar, so kind of an interesting question, but no. And writing, I did typing. Okay, number 19. Prove. Write a 2-column proof. Okay, write a 2-column proof by the side. Oh, here's the side angle side proof thingy. So I can't guarantee I'm going to be very good at this. Given what you have there, prove what you have there. Given angle A congruent to angle D and AB over DE similar. Okay, at least they drew them the same way. I'll keep the drawing on that side. I'm going to do stuff on this side, and I'm going to do my best here. With the side angle side similarity theorem, remember that we can't use side angle side similarity in our proof. We can use side similarity in our proof because that's already been proven. So within scope, that'll be okay. And we're probably going to do, how did they do it before? They drew like a PQ. If you were with me on the lecture portion, then we read out loud that they like made this thing by like drawing a PQ in here that's parallel to AC. We'll probably do all that stuff again and prove triangle congruence and then go based off of that. So let's see. So let's start with our givens. We're given that angle A is congruent to angle D. and that AB, I don't know if I want to write these in the same thing, but AB over DE is equal to AC over DF. So that would generally be what we say for, hey, the triangles are similar by side angle side, similarity. But we can't use a property, we can't use a theorem to prove itself, right? That's the thing. All right, so the next thing that I want to do is I want to draw that PQ thing, right? So let's do this. Let's make it look as such that we have some PQ inside here that would give us the same length on one of these parts here. So let's do it right, I guess, like this, where the DF, are these kind of the same height? Not really. Let's draw like a PQ like that and pretend like that's the same length for these things. So let's call this PQ. I want to make it parallel to this AC, and I want to make P a point on AB so that you have some equal length parts. Like AP is the same length as DE, stuff like that. So you mean AP. Actually, I don't want to do that because that doesn't give, let's see. I want to make this triangle in here. Here, let's do this the other way. I want to make this triangle here go like this so that A and D are on the same point, right? So I want to do PQ like this rather. So let's do PQ. Now I can make AP the same as DE, and these will be parallel here. I don't know how to write that. What? So draw, y'all gotta draw some segment PQ. We called this the parallel postulate, I believe. Draw PQ so that P is on segment AB. Q is on segment AC. And then we want those to be parallel, PQ and BC. PQ is parallel to BC, and that we have AP equal to DE. That's the parallel postulate. Now that we have that, now that we have parallel bits, we can say some angles that are going to be congruent to each other, such as APQ right here, and ABC. We're not really looking at this one just yet. We're going to do something after that. Those are corresponding angles now that those lines are parallel, right? We have those two lines parallel. So I can say angle APQ is congruent to angle, whoops, that's a triangle symbol, is congruent to angle ABC by the corresponding angles theorem. Okay. Angle A is congruent to itself by the reflexive property. And we don't need to mark, well, here, let me do 2 marks for these ones here because I don't want to say it's congruent to that one that's already marked. Angle A is congruent to itself by the reflexive property. So basically what I'm starting to build up right here is I want to kind of do a angle-angle similarity here. So I have 2 sets of triangles that are similar now, APQ and ABC, like that. However way I want to write it. I'll just do that. So triangle APQ is now similar to triangle ABC by using angle-angle. I know that was part of the last section, but I mean, it's what we do. Angle-angle similarity theorem. Okay. Now that we have that part, we know now that corresponding side lengths would be proportional. So which ones would be in proportion with each other? We have AB over AP, AB over AP. We have AC over AQ. I'm going big to small. AC over AQ. And then let's go alphabetically. Let's go BC over PQ. Now, I don't know if we say something like corresponding, what did I say before? Corresponding angles of similar triangles are congruent. Corresponding sides of similar triangles are proportional, or any figures, right? So corresponding sides of similar triangles are proportional. Corresponding sides of sides of similar triangles are proportional. That's how I'm saying that. I don't know. CSSTP. I've never written that before either. This looks like it's going to be kind of a longer proof, so let's just keep extending this down. So now that we know that those things are in proportion to each other, let's see, what can we do there? Now that we have the proportionality, let's align that back with what we know about AB over DE, right? We have a given up here that these two are equal, AC over DF, but now let's use it more with our new PQ triangle that we have. Where's AB and DE? Right here and right here. AB over DE should be the same thing as, what other thing that's in proportion? Any other set? Let's do the ones with the AC and the PQ things, AC and DF, but we don't know that, oh, we do know that AC is the same as DF. But let's do a substitution. Let's say how AB over DE, wait, that's how they wrote it before, right? Let's do big to small, AB over DE, and that's the same thing as AC over AQ. AB over DE is the same as AC over AQ. If we're doing a substitution, we're trying to relate these two things, these two different sets of triangles, because we're bringing back the DE thing, if that makes sense. So this will be a substitution. Property of equality. And in doing so, we can have a way of relating AC now in two different ways, because AC over DF is AB over DE and AC over AQ is AB over DE. Those are two different ways that we have that written, so we have two different ways that they can compare. So let's multiply both sides by AQ. So AC would be, I don't know how to write this best, AB over DE times AQ. And we can do it from the one that was above. We can multiply both sides by DF here as well. And we get, basically I'm doing a cross multiplication here, but what I'm eventually going to do is I want to write how AQ and DF, I'm going to figure out how AQ and DF can be written as the same thing, because you're going to see that they will align, basically. They'll have the same appearance. So what did I say? Multiply by DF, AB over DE times DF. And we have to do one step at a time of these, unfortunately. This is the multiplication property of equality. Multiplication prop of EQ. The first one before was substitution property of equality, by the way. And now, we can also, I guess this is also multiplication property of equality. I'm going to multiply by the reciprocal, DE. I'll just write it to start with DE over AB, which would cancel those out and bring it to the other side. I'll get AQ and DF to be the same length. So AQ would be, I'll write AC. So AC is here times DE over AB. And check this out when we do it on this other one. It will also be DF equal to AC times DE over AB. So that's also multiplication property of equality. Multiplication property of equality. I multiplied by the reciprocal. It's division, but also multiplication by the reciprocal is a way to put it. So now you can see that these are both the same ratio. So AQ and DF are equal to each other. If they're equal to each other because they're equal to the same thing, that's the transitive property of equality. Now, if they are equal to each other, then their segments are congruent to each other. So 11 segment AQ is congruent to segment DF. So there's a lot of math to get one set of things congruent to each other. That's the definition of congruence. And if I have those two congruent here, now I can mark that up. AQ is congruent to DF. Is there a way that I can say AP is congruent to DE? Was that given? AP equals DE? Oh, we wrote this before. AP is DE, so that would be the same thing. Let me do this on this step. AP segment, I probably could have written this a long time ago, but I didn't know where I was leading myself to. AP is congruent to segment DE, not AE. AP is congruent to segment DE. And let's mark that one as well. So it was a lot of work to get into those two bits congruent. We know, well, I don't know if we said that angle A was congruent to angle D. Did we say that before? That was a given. So angle A congruent to angle D. Duh, it's a given. So we have two sets of sides that are congruent, boom, 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 and the angle in between that's congruent, that's enough to say that those two triangles are congruent to each other. It looks like we're leading better into what we have here. So these two triangles are congruent to each other. Let's call them PAQ. I don't know. Triangle PAQ is congruent to triangle that's EDF. I probably should say APQ. Oh well. EDF. This is side angle side congruence, not similarity. Side angle side congruence theorem. Okay. So if that's the case, whenever we do some sort of side angle side congruence stuff, we often want to do CP/CTC after that to work it out. And what does that mean? It means PQ and EF are congruent to each other. Let's use purple. PQ is congruent to EF by CP/CTC. This is important because we're going to start to do some sets of correspondence with proportionality. We're going to show that we have side-side-side similarity, right? We can prove side angle side using side-side-side, and kind of that's the goal that we want to do. If PQ is congruent to EF, then PQ equals EF. That's once again definition of congruence. But the other way, we went from congruent side. Let's try to extend this. We went from congruent sides. Excuse me. Before equal sides to congruent. Now we're going congruent to equal, if you will. Now we're trying to look at triangle ABC and triangle DEF together. Now PQ is kind of out of the picture, where we can build the same proportionality that we had before through a substitution of parts that we have. So if you imagine here, we can substitute because PQ is EF, because AQ is DF, and because AP is DE. Let's have DE, DF, and EF substitute for AP, AQ, and PQ. And we have this one to write that for. So let me copy this statement down here. I'll get rid of the sixes, and let's substitute those guys in there. So this will be a substitution of the bottom parts. Now that we know that those are all those lengths, we're going to use side-side-side similarity on this. This is a tough proof. AB over, I hope I didn't mess anything up. AB is equal to, where's AB? Excuse me, not AB. Wait, hold on. What did I just erase? AP, AQ, PQ. AP is equal to DE. So substitute. AC is equal to, did I say AQ? I think I said AQ. So AQ is equal to DF. And then PQ for BC is equal to EF. So that is a substitution of the bottom part. Substitution property of equality. And if those are so, if these are in proportion, check that out. AB in proportion with DE. AC, and I wasn't looking at the diagram, now I am. AC with DF and BC with EF in proportionality. Those are in proportion, therefore these two triangles are similar. Which ones? ABC, I'm looking at the proving statement. Triangle ABC is similar to triangle DEF by side-side-side. Similarity theorem. So I proved side angle side similarity theorem using side-side-side similarity theorem ultimately. Whew, that was not easy. That was a lot of steps, and I hope that I did that right. I was not a fan of that problem. No more proofs, please. We have 5 more problems, and hopefully none of them are proofs. Number 20. How do you see it? Never assigning that problem to my kids. Which theorem could you use to show that triangle OPQ, boom, I don't know what I'm drawing there, is similar to triangle OMN in the portion of the Ferris wheel shown when PM is 5 feet and MO is the same as NO, congruent, which are 10 feet. So 10 feet and 10 feet. Oh my gosh. Which theorem could you use to show that they are similar? Well, oh, what was that one? Did we learn this yet? I mean, this would be a side angle side thing because of this thing here. Oh, PM is equal to QN. I didn't see that. I was going to say, was there one that we learned that said that this split part should also be the same for whatever thing? We might have with triangles, but now that we show that that's there. They don't ask us to explain, but guys, we would be using side angle side. Congruence theorem would be used to show triangle OPQ is similar to triangle, I mean the Ferris wheel has nothing to do with this, similar to triangle OMN, because you would say the angle O is congruent to itself by the reflexive property. That's the included angle. And then you would compare these side things. Now these are both sets of isosceles triangles, so it wouldn't really matter which set you compare to another, but I would try and see that OM is to probably OP as ON is to OQ. Whoops, OQ. And it would work out because 10 plus 5 is 15 for both of those. Sorry about that. Let me do that one more time. OQ as 10 over 15 feet is the same as 10 feet over 15 feet. So that would all check out. That would be a side angle side test. So boom, boom. It all works out. Anyway, there's that. Number 21. Drawing conclusions. Explain why it is not necessary to have an angle side angle similarity theorem. I actually brought this up. It was probably during the lecture portion. I didn't intend to bring this up, but I did. I want to type it, but I want to write 21 first. Okay, hey, it is not necessary to have an angle side angle similarity theorem because angle angle similarity theorem already exists. Meaning angle side angle means you need two sets of angles to be congruent and a set of corresponding sides to be the included set of corresponding sides to be proportional. We don't need the set of corresponding sides for that, but that's the reason. That's the reason. All right, number 22, thought-provoking. Decide whether each is a valid method of showing that two quadrilaterals are similar. Justify your answer. Okay, so this can be tricky because sometimes I feel like I would know, and then I don't really necessarily know for some of these. I got to think about what we can have. Basically, I'm going to try and disprove them, and if I can't disprove them, then I'm going to say maybe yes. So A for side angle, would that be enough? And what this means here is if you have like two quadrilaterals here, say these sides are similar, then angles are congruent, then sides are similar, then angles are congruent, like that. Again, they grow in proportion in a certain way. Not congruent, but in proportion to each other. I'm thinking I can have... Let's do... If those angles are congruent, they grow in proportion. Those other angles can totally change, right? I could totally do, like for example, let's say that these were right angles here. That's the easiest way to kind of build it. Let's say that I have right angle here and a right angle there. So I'm kind of tilting these on their side. So sets of right angles here. I'm going to grow this one bigger. And we have proper proportionality among these things. So this one also grows bigger here. So similar or proportional, great. But I can totally change these other parts, right? This can look like this, and this can look like that. There's no problem. So A is a big fat no. I can totally manipulate these sets of angles and these sets of sides here despite the other two things being congruent. Basically, these would be trapezoids, right? Trapezoids here, and I could totally change all those other things. So part A, probably definitely not. Side angle, side. Suddenly, let's try the trapezoid thing here. Three sets of sides proportional and angles congruent. Let's do the same trapezoid bit where I have right angles there. This one's kind of hard to like write as justification, but I have boom, boom. Let's make that kind of like, hey, this is 3 times as big, so let's make this kind of 3 times as big. Now in side angle, side, these have to be in proportion as well. So if I have this one, oh, I messed up the squigglies, but let's do it like that. Suddenly these grow in a certain way where now these kind of lock in place in a way that now these angles I think have to be rigid, right? It's 3 times as big, 3 times as big, 3 times as big over here, and then these angles in this trapezoid would work in a certain way that these would have to lock in place. I think that would be a yes. Yes, because the fourth pair of sides have to be proportional, and the angles would have to be congruent, right? These would have to be in proportion, also 3 times as big. Fourth pair of sides proportional. And like I said, these other things would lock in. I'm not doing a full proof or anything like that. I'm just kind of giving my idea of, can I change things? And other angles would be congruent. Angles would be congruent. That's my thought on it, at least. Part C, side, 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 side. Absolutely not. Side, 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 side. We see things with... Well, we did it with angles for things before, so let me just guarantee this. But side, 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 side. Look, I can take, like, not parallelograms, but I could take things that would have to go in different directions. Like two well, not rhombuses, but... I mean, here, look. Let's use the case of rhombuses. If I have a rhombus... I have a rhombus shape. If I have a rhombus that looks like, say, like this, and these are like side lengths 2, I'm not going to do squigglies, I'm going to do 2s here. And then I have another rhombus that, you know, I double these to like 4s, right? They're double, but the angles can totally change, right? I double them, so it's a clear no in this case because angles could change. So, right, these could all be right angles, right? It could be a square, and then suddenly this one's not a square anymore, so absolutely not. Part D may be a yes. Let's see. Side angle. Side, 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 side. Now we do... I still don't think so. Not 2 rhombuses anymore, but... because then things would lock in place after that. Let's do this kind of instance. I have this shape here. Let's grow it. Let's enlarge it. In a way. I'm going to change some things up. Let's say that we have all 4s... in here, and these two are congruent. But do these 4s... Oh, I guess they don't have to be 4s anymore. Ooh, how do I change this? Imagine that... Maybe this would have to be the case. Let me think about... Instead of rhombuses, because that's what I'm saying, right? These can't be 4s anymore. Let's go, because I wanted to do something like this. I wanted to extend these and do more like a kite-looking thing. But these would have to grow in proportion as well. I'm just trying to think if I can morph my kite. Ooh, could I do that? No. I'm trying to think how I could morph the kite in a certain way to make it different. And by the way, this isn't part of this shape, so I should ignore what I'm doing there and keep the other ones as they were. So keep this as it was. I want to do something with 2 kites. If they had proportional sides and 1 pair of congruent angles, but yet not be similar. Oh. Let's do the angles congruent not at one of the ends of the kite, but at another end set. So let's say we had an angle measure here that was congruent instead of the ones on the ends. So not by symmetry, but by this. So let's lock that in place and grow these sides in a certain way. But suddenly, this other one... I'm trying to find a way to say no. Maybe these have to lock in place. So like 2, 2, and like 3, 3, whatever. They're not drawn to scale clearly. And let's double these, like 4, 6... Well, okay. I don't think this one necessarily has to be a kite then. Can I make a 4 and a 6 in a certain way, but change its nature of the 4 and the 6? I feel like you can. I just don't know. Let's see. I have to dispute it if so. Hold on. I'm going to pause and think about this one. I want to get this right. Okay, well, I'm thinking about it, and the only thing I'm thinking almost that it would be the case, but the thing that I'm thinking about right now is not that these angles have to be the ones that correspond to be congruent. You can have side proportionality, but the angles can be, I think, in any set. So, for example, it can be these angles that are congruent here, which can then totally morph your kite, right? So I feel like because of that, that would be a no. It's not that they have to correspond in terms of orientation like that, because the angles could be in different spots and therefore the kite can change. This is not a quadrilateral similarity statement. This is a justification for similarity in quadrilaterals. So it's not that parts have to correspond like that. In this one specifically, the side angle, the angles have to be between your sets of proportional sides. And this is true here for one set of angles between sides, but they don't have to be the parts that correspond. Like, this doesn't have to go straight to that, basically. So I think it's a no for that. If these had to lock in here and be congruent in those sets, then I think it would be a yes. But I think besides that, I do believe it's going to be no. Now I'm just going to lean on that. All right, number 23. Writing. Can two triangles all have all three ratios of corresponding angle measures equal to a value greater than 1, less than 1? Next week. Can two triangles have all three ratios of corresponding angle measures equal to a value? What? What are they saying? Can two triangles have all three ratios of corresponding angle measures equal to a no. No for either. Let's see. Two triangles cannot have all three ratios of corresponding angle measures equal to a value greater than 1 or less than 1. For one, they would not be congruent anymore, and corresponding angles have to be congruent in similar triangles. For another, if this was the case, then angle measures in a triangle would no longer add to 180 degrees. That's the reason why the triangles, the thing that I keep bringing up, or like that I bring up whenever I talk about triangle similarity, is like, just because you make a triangle twice as big doesn't mean the angles get twice as big. It doesn't suddenly turn into a hexagon and triangle angle sums is still 180 degrees. It always has to be. So that's just kind of a thing. All right, last one, number 24. Use a diagram to show why there is no side-side angle similarity theorem. Well, it's probably going to be the same thing when you talk about side-side angle congruence, or angle side-side is how I bring it up. And the main one that I tend to bring up for at least congruence is this case right here. Say that I have, for example, and again, this is congruence first. Say that I know that this angle is locked into place, and then this side is here, and then I have another side here that's congruent to a third set like that. Hold on, I did this the wrong way. Let's make it smaller. I have a third thing right here that's locked in and congruent, right? And then I do another triangle with the same information, and I know I'm doing congruence first, but I do a triangle with the same information, but I bring this side over here instead. It's still congruent to that third side, but it shortens this, which is allowed, right? This would be this kind of case. I could do the same kind of thing if I just grow these out bigger now. So let's take this and just boom, boom, and take this and just kind of lock it in place like that. So we have a case here where the angles are congruent. I'm going to kind of shrink that to make it look like a similar looking arc thing. And these are in proportion, right? We can say twice as big or whatever. But this is a drawing that disrupts that because the way that these angle measures change like that. So congruent triangles show that that's not necessarily going to be the case in angle side-side. They say side-side angle. Wish I saved that sneeze for after recording. And so that's a case that does that. Side-side angle, similarity, no good. You can see how the side lengths here change, the angle measures here change, and that's it. All right, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. We cracked it within a 90-minute time frame. being section 8.5, we have one more section on 8.6 on the triangle proportionality theorem. I also sometimes call it the side splitter theorem, so forgive me if I ever say that, but that's for later. Check out, again, the description section down below if you want to follow along with anything here, from timestamps to PDFs to all the stuff. No graph paper needed for this one, but this tied in a little bit with section 8.4 in the way that this was all about triangle similarity. We did talk about angle, and we're good to go. Like I said, one more section in the chapter. That's it. Thank you. Take care. I will see you in the next one.